All right, so we're going to start to get into working with polynomials and the complex numbers that can be solutions to some of those things. So we've already kind of gone through this. So let's look at this example here. We have these binomials. A couple of them actually involve some imaginary numbers. We have negative 5i and positive 5i. We're going to go ahead and multiply this out, simplify it as much as we can, and see that this actually is equivalent to a polynomial that has only integer coefficients, whole number, positive and negative coefficients. So let's go ahead and multiply out this first one. We're doing x times x times 5i, negative 5i times x, negative 5. All right, so that's x squared plus 5ix. Negative 5i times x is negative 5ix. And then negative 5i times 5i is going to be negative 25i to the second. Remember, I to the second is really negative 1. So I can kind of cross that out. All right, doing a little bit of simplifying here. I've actually got positive 5ix, negative 5ix. Those two things can actually cancel each other out. And then here with negative 25 times negative 1, it's going to end up giving us plus 25. So these two here, when they multiply together, even though they had imaginary numbers in them, I actually got no imaginary numbers at the end with this result. And now we need to further multiply that by x plus 2 to finish this off. The reason that happened is because these are conjugates. Anytime you multiply two conjugates with imaginary numbers, so something like a plus bi times a minus bi, we actually don't end up with any imaginary numbers at all because, right, when we think about this, this ends up being a squared minus b squared I squared, right? And so that I squared is a real number. So no more imaginary numbers involved. All right, let's go ahead and finish this out. X squared times x is x to the third. X squared times 2 is 2x squared. 25 times x, 25x. 25 times 2 is 50. So here, no like terms. This is actually just our final answer. Is a polynomial that has only real number coefficients. 1, 2, 25, 50. No imaginary numbers at all, even though in this factored form, we can see there are actually imaginary numbers. And if we remember what factored form lets us do, factored form lets us actually find the zeros of a polynomial. So this actually, if we kind of say, what are the zeros of this polynomial? Well, then I know that by solving this equation, I can find one of my zeros. One of my zeros is going to be positive 5i. It's going to be an imaginary number that is a 0 for this polynomial. Likewise, this one would also give me another 0 of negative 5i, and this one would give me a 0 of negative 2. So I have 3 zeros to this particular polynomial, only one of which is actually a real number, and 2 which are, in this case, imaginary numbers, purely imaginary because there's no real component to it. So we're going to be looking at how to discover these either imaginary or complex solutions, not just the real solutions. We've already talked quite a bit about how to find real zeros to polynomials. We also want to investigate what are some of the other zeros that exist in the complex numbers. All right. So that gets us to the fundamental theorem of algebra. So it's not really the beginning of algebra. It's kind of a little bit of a misleading name, but a polynomial with degree n has n zeros. So far, previously in chapter 2.3, we said it had up to n zeros. But if we include the complex numbers, there actually are going to be n zeros. Now, that doesn't mean they're all different from each other. Remember, some of our zeros can have a multiplicity. They can show up more than once, meaning the same factor will be a factor multiple times, thus giving us the same 0 multiple times. And some of our zeros will be complex numbers, not just real numbers. So we're going to have to expand our repertoire in terms of how to find these zeros. But there will be exactly the number that the degree is. That's kind of cool, really nice for knowing that we're done solving, right? If it's a fourth degree and we find 4 zeros, then we're done. But if we haven't found them all, then we have more work to do. Okay. So let's look at a polynomial with this 0. So this is just a bit of a review. These are all real numbers. Remember, each of these zeros represents a connection to a factor, right? X minus 3 is going to represent a factor of x plus 3, right? Because if I plug a negative 3 in here, and that's going to cause this to be 0. And then when we multiply by the other factors, obviously multiplying by 0 turns everything to 0. This one, x minus 0, or just x, would give us a factor that. 2 would be x minus 2, and 3, x minus 3. So this is the factored form. And all of these zeros on our graph would also show up as x-intercepts. So we would be able to visually see these if we had graphed this equation. That's not going to be the case with complex zeros. Complex zeros are not going to show up on the graph. And so we're going to have to use some algebraic techniques for finding those. All right. Find all the zeros of this polynomial. So there's many ways that we could go about this. Sometimes our polynomial may be factorable. In this case, there is a little bit of factoring that we can do. We may need to take a look at the graph. So here's a graph of it. We can see one of our intercepts at 0, right? X equals 0 is one of our intercepts. So that's a real 0. I don't see any other x-intercepts. And this is a degree 3 polynomial. So this is telling me I've got one real. And I'm going to have 2 that are non-real. Whether those are imaginary numbers or complex numbers, I'm not sure, but 2 of them are going to be non-real because I need to have a total of 3. If I only see 1 that's a real number, it means the rest are going to be not real. We could go about actually figuring out how to kind of attack those in a couple ways. This one is factorable. So I'm going to do it that way first. I can take an x away from both of those, leaving me with x squared plus 4. So this is our, when we're trying to solve this to figure out the zeros, this is one of them, right? X equals 0. That's good. We saw that on the graph. We see that right here. It's this other one that's a little bit trickier. We can actually solve this equation, right? This equation is solvable. There's not even any factoring that's necessary here. We could just subtract 4 from both sides, get x squared equals -4, and then take the square root of both sides. And the square root of -4, remember when we're solving, we need to say plus or minus. We take the square root of this as though it's positive, so that's 2, and we stick an I on it. So plus or minus 2i. So those are our other 2 zeros, 2i minus 2i. In this case, that would kind of be the best way to go about it, is just solving this equation. If this was a quadratic that was not factorable, then we may want to use like the quadratic formula, which we will do a couple times here later. But when it's something like this, just kind of solving for it is probably the most straightforward and easier way to go. So there we go. We had a polynomial of degree 3, and we found all 3 zeros. Since we know the zeros, we could also write the factored form, which is something we're going to talk about in a minute. But our factored form in this case will be x, that represents this 0. And then x minus 2i represents this 0. And then x plus 2i represents that one. These are all what are called linear factors, because x is just to the first power. And there's 3 of them for a degree 3 polynomial. That's actually an important theorem that we'll look at in a moment. So let's go ahead and take a look at this one. Same idea, find all of the zeros. This one, unlike the previous one, is not, I don't see a good way to factor it, so I'm just going to kind of glance at the graph, see what the graph looks like. Awesome. I see a 0 at -1. I also noticed that this 0 has some odd behavior. The graph isn't just passing straight through it. We have that bounce. Remember, when we have some bounce, that means that this 0 actually has an even multiplicity, meaning this 0 shows up some even number of times, probably 2 in this case. I'm going to guess 2, but it could be 4 or 6 or 8. We know that the multiplicity is even when we see this sort of bounce. So since I know a 0, I can actually factor this polynomial using synthetic division. So that's what we're going to do here. I'm going to use -1, that's our 0, and I'm going to set up synthetic division. So I have a coefficient of 1, 2, 10, 18, and 9. Bring down my first one, -1 times 1, add these together, -1 times 1, add these together, -1 times 9, add these together, -1 times 9, add these together, remainder 0. Obviously, we were expecting remainder 0 because it was a 0. And this would be our reduced polynomial. Reduced by 1 power, so it'd be x to the third plus x squared plus 9x plus 9. Again, since this had a multiplicity, an even multiplicity, I'm going to need to factor this one out again. Because I factored it out once, I've essentially factored out the linear factor x plus 1 that goes with that 0 one time, and I was left with this. I need to factor it out again, so I'm going to do that. I'm going to use these, so that's 1, 1, 9, 9. I'm going to use the reduced polynomial. Again, I'm expecting remainder 0. 1 down, -1 times 1. Add these together, I get 0. -1 times 0, 9 plus 0. -1 times 9, -9. Remainder 0. Awesome. So it factored out twice. So this did at least have a multiplicity of 2. Now what I see here, I've factored out two factors, x plus 1 twice. So now I've reduced this power 2 times. I actually have a polynomial that is now x squared plus 0x plus 9. This polynomial is irreducible. It's not factorable, can't do anything. I can see there are no real zeros to it because there are no other real zeros for this. And I'm pretty sure -1 isn't going to work again. So what I need to do now is figure out what the zeros for this polynomial are. And this is just like that equation we had on the previous example. I'm going to subtract 9 on both sides, get x squared equals -9. When I take the square root here, I'm going to get plus or minus 3i. So those are 2 more zeros to bring our total up to 4, right? -1 showed up twice, and now I have positive 3i and negative 3i. I have 4 zeros for this 4th degree polynomial. And my other linear factors would be x plus 3i, x minus 3i. So I have 4 linear factors now. This one showing up twice, and these ones showing up once, for a total of 4. Cool. And those are all of our zeros, right? Our zeros are -1, -1, 3i, -3i. Those are all 4 zeros for this polynomial. All right, so I've been stating this a lot, linear factors. So a polynomial of degree n has precisely n linear factors. And we've been showing that throughout. Each of these represents a linear factor. These could be, well, they can all be complex numbers because a real number is a kind of complex number. So these are all going to be written in this way. Sometimes they're going to repeat. We can use exponents to show repeating multiplicity of a particular factor, or root. Yeah, some of these are going to be purely imaginary. Some of these are going to be purely real. Some of them are going to be complex. Just kind of depends. All right. Complex zeros occur in conjugate pairs. This is a really important idea. Whenever you have a 0 that is a complex number, then you know that the conjugate of that complex number will also be a 0. That's very, very useful. The reason this is the case is because if we want our polynomial to have real coefficients, so if it's like ax to the third plus bx squared plus cx right? Something like this. And we want these to be real numbers. If we don't have conjugates that are complex numbers, then we're still going to have i's involved in our problem. And that means we no longer have real number coefficients. We have coefficients that involve imaginary numbers, thus not really being able to graph it on the real number plane. So whenever we are dealing with a polynomial with real coefficients, we always know that our complex zeros have to be conjugates. That way, when the conjugates multiply together, we actually get rid of those imaginary numbers altogether. That's also true for purely imaginary numbers. So if we have a root of 2i, that means that negative 2i will also be a root. That's because as a complex number, this is written as 0 plus 2i, which means 0 minus 2i will also be a complex, will also be a solution, right? It's the conjugate of that. Doesn't work the other way. If 1 is a root, that doesn't mean that negative 1 will also be a root, right? That's just crazy, right? Because this is 1 plus 0i. So that implies that 1 minus 0i is a root, but these are just the same number. They're just 1. So if 1 is a root, that means 1 is a root. So it doesn't work with purely real numbers, but it does work with imaginary numbers. So if we have a positive imaginary number, that means the negative imaginary number will also be a root, a 0. All right. So here we go. Let's take a look at this. We have a 5th degree polynomial. Just kind of taking a look at it. We know there's going to be 5 zeros, there's going to be 5 linear factors. I can only see 1 on the graph, but there's a wiggle. As it passes through, it's doing that wiggle. Anytime it wiggles, that means we're going to have an odd multiplicity. Maybe 3, maybe 5, could be 1 also. There are some cases where it kind of looks like a wiggle and the multiplicity is only 1, but I'm inclined to believe maybe 3. That way there's only left over that are 2 that are going to be non-real. So we're going to take a look at this on the next page, and we're going to try to factor out this 0 multiple times, 3 times, and see if it works all 3 times. So let's go ahead and do that. So remember, we had a 0 of x equals 2, and we think it has a multiplicity of 3. That's what we're kind of thinking based on that graph. So synthetic division 3 times. Obviously, each time we do this, we'll reduce it and make it a little easier. Didn't even give myself enough space. All right. Take our time with this. Make sure we don't make any mistakes. 2 times 1 is 2. Negative 8 plus 2. 2 times negative 6. Add those together. 2 times 16. It's going to be negative 24. That's going to be negative 48. 16. 2 times 16 is 32. Cool. 32, negative 2. Right. So that was great. We knew that it was going to be 0 because we did know that this was at least a 0 one time, but we suspected 3 because of the wiggle. Obviously, this is now a 4th degree polynomial, and we factored out one of our factors of x plus 2. Okay, so now we're going to work on that again. Same factor, and we're going to use this reduced polynomial. Okay, going through this. 2 times 1 is 2. 2 times negative 4. 2 times 8. Negative 8. 2 times negative 8. Negative 16. Yep, remainder 0. Okay, so since it happened twice, we're sure it's an odd multiplicity, so it's going to work again. Let's do it one more time here. I don't like that space there. Let's do this, I guess, right over here. So again, we're using this reduced polynomial, so that's 1, negative 4, 8, negative 8. 2 times 1 is 2. 2 times negative 2. 2 times 4. Okay, awesome. Worked 3 times, so it was a multiplicity of 3. So this factor, it has a multiplicity of 3. And now we need to figure out what the other ones are. So I'm going to actually delete some of this stuff. I want to get rid of that to give myself some more space. I have this reduced polynomial down here, this one right here, which is x squared minus 2x plus 4. So I've reduced it 3 times by this factor. I want to know what the rest of the solutions are. This is not factorable. We could sit here and we could try it, but I know it's not factorable. And since we didn't see any other x-intercepts, I actually know the solutions to this are not going to be real. I can't solve this like the other ones because I have this middle term of an x. I have an x squared and an x, so no way to kind of get there. The only thing I can do is quadratic formula. So remember, quadratic formula, x equals negative b plus or minus square root b squared minus 4ac all over 2a. So if I have something not factorable, can't solve it the other way, got to go to quadratic formula. So negative b is going to be 2 plus or minus square root b squared is 4 minus 4 times 1 times 4, so that's minus 16 all over 2 times a, which is 1, 2. Here we got negative 16, so that's 2 plus or minus, 4 minus 16 is negative 12 over 2. Square root of negative 12, this is going to be 2 plus or minus 2 root 3i over 2. Both of those are divisible by 2, so we're going to get 1 plus or minus root 3i. These are our other 2 solutions, complex solutions, real part and imaginary part, one of them plus, one of them minus. So we could write out the linear factorization, including this one. So it would be x plus 2 to the 3rd power, 3 of those, and then x minus 1 plus 3 root 3i, and then x minus 1 minus root 3i. So those are our 5 factors, obviously a multiplicity of 3, 4, 5 of them. Pretty complex. That'll be the end of part